Guys, let's take a few minutes and look at the solutions to the practice problems about a two-proportion z-interval and two-proportion z-tests. So for question number 9 about the proportion that tweet within different age groups, for the conditions, we have two independent random samples. They're independent of one another because they're from completely different age groups. So we need to check the 10% rule here because this is an observational study. So certainly there are more than 3,160 internet users in the age group of 18 to 29, and certainly more than 5,321 in the age group of 30 to 49. And the point of this here is to make sure that the individuals within each sample can be considered independent of one another. So one of the things that makes this question important and a little bit different is the way the information is presented to you. Because in the question, you are presented with the percentage out of the 18 to 29 age group that use Twitter and the percentage out of the 30 to 49 age group that use Twitter. What that means is you have to calculate the success and failure counts. And that's actually very important because to complete the test, or to complete a confidence interval, you have to enter the success counts into the calculator. So notice in the group 18 to 29, 26% of 316 is 82. That's greater than or equal to 10. And in the age group, let's do the failure rate. So if you take 316 minus the 82, that gives you 234. That's the failure rate in the 18 to 29 age group. So in the 30 to 49 age group, you've got a total of 532 people. The 14% that use Twitter, 14% of 532 is 74. So if you take 532 and you subtract the 74, that gives you the failure count of 458. So all of those counts are greater than or equal to 10. So the normality condition is met. So first, let's go back and look at how the standard error is calculated, because this will explain the two different ways in which independence is being used in this question. So this is the fancy work for the standard error, and I'm going to show you the simpler work in just a second, but what you're looking at on the screen right now is how we would have done this question if we went back all the way to the random variables unit. So notice right here, this is the formula, the square root of p hat times 1 minus p hat divided by n. So this is the standard error for the, this is the standard error for the sample from the 18 to 29-year-olds. So we had a 26% rate of 18 to 29-year-olds using Twitter. So there is the p hat. Here's 1 minus the p hat, so 1 minus the 0.26 gives you 0.74, and then we're dividing by the sample size for that group, age 18 to 29. So that's the standard error for that particular sample. So the 10% rule, it's important that it applies in the 18 to 29 age group because that is what justifies the calculation of this standard error. Then we have the same thing in the age group 30 to 49-year-olds. So this is again the same formula, the square root of p hat times 1 minus p hat divided by n. This is the standard error for the sample from the 30 to 49 age group. And in that age group, the rate at which we observed them using Twitter was only 14%. So there's p hat. Here's 1 minus p hat, 86%, divided by the sample size from that age group. So it's also important that the 10% rule apply to this age group's sample, because what that does is it justifies the use of this formula for the standard error from that particular sample. So notice these standard errors are just really standard deviations. So the reason that we can take this standard deviation and this standard deviation, we can square them and then we can add them, and then we can take the square root. The reason that we can do that is because we believe that the sample from 18 to 29-year-olds and the sample from 30 to 49-year-olds, we believe that those samples are independent of one another. We have random samples that are independent of one another, two independent random samples. So because of that, I can combine these two standard errors the way that we did in the random variables unit. And when you do that, notice what happens then. The radical and the square for both of these standard errors, they're canceled. And what that ends up giving you is this formula down here, and this is the formula that you would see on the formula sheet for the standard error when you are looking for the difference between two proportions. So notice all that we're doing is taking what's under the radical and using that in our calculation, because the radical and the square have canceled. So it's just the 0.26 times the 0.74 divided by the sample size for 18 to 29-year-olds, and the same thing, the 0.14 times the 0.86 divided by the 532. Again, that's just what's under the radical in the calculation for the 30 to 49-year-olds. So again, the reason for showing you this up here, this is the way we would have combined with two independent random variables. This is the way that we would have found the standard deviation of the difference between two independent random variables. Well, the truth is that's really what's going on here, because this is the p hat from a random sample of 18 to 29-year-olds. That's a random variable. This represents the standard error for the p hat from 30 to 49-year-olds. That is also another random variable. And in this context, we're looking at the difference between those two random variables. So if they are independent of one another, which was one of our conditions, I can take the standard errors and square them and add them and take the square root. This is just the simplified formula that you have on the formula sheet. I just wanted you to see how this connects back to what we did with random variables, and I wanted you to see why there are two ways to think about independence. The 10% rule justifies these individual calculations, but having two independent random samples is what justifies squaring them and adding them and then taking the square root, so we can combine these two independent random variables. So this is the standard error of the difference between these two sample proportions. And what that simply means is it's interpreted like any other essentially standard deviation. So that is telling us that typical, that word is important when you are interpreting standard deviation. Typical differences between sample proportions will be within 0.029 of the true difference between these between proportions. So going on then to 9b, let's construct and interpret the 90% confidence interval. So this is the 90% confidence interval using the TwoProportion zInterval command. So notice you had to calculate the success counts and the failure counts for each group to enter the data into your calculator. So I want to show you that now. So notice if you look at the TwoProportion zInterval command on the calculator. So to do that, we'll press Stat, we'll go to Tests, we'll scroll down. It takes a second for me to do that on the emulator. And I went too far. There is the TwoProportion zInterval command. So notice into this calculator, into the command, you have to enter the success count and the sample size. So notice for the younger age group, the success count is 316 times 26. That's 82 out of 316. So I will enter that first. Now I have to have the success count from the older age group. So that's 14% of 532. That's 74 out of 532. And our confidence level here, this is a 90% confidence interval. And so we'll highlight calculate and press enter. And there's the confidence interval. Essentially, the confidence interval has a lower boundary of about 7.3% and an upper boundary of about 16.8%. And that's exactly what we see here. So we should just interpret it then. So we are 90% confident. When you say that, you are stating the accuracy level of the method being used here. 90% confident that, and then copy the words. The difference between the true proportions of adult internet users in these age groups who use Twitter. Please copy the words. That's the best way to make sure that you have the parameter described correctly, or in this case, the difference between the two parameters described correctly. And then that difference is between, here's the lower boundary, 0.073, and the upper boundary, 0.168. So the last set of questions, these last three questions all use the same context. Do the data give convincing evidence of a difference in the proportion of all Illinois high school freshmen and seniors who have used anabolic steroids? So something to think about. The word evidence, that's what signals to you that you should complete a significance test, in this case, a two-proportion z-test, rather than building a confidence interval. Remember, when you interpret a test of significance, when you write the conclusion for a test of significance, in the very last sentence, you should always use the word evidence. So one of the reasons we ask you to do that is so you get used to looking for that word. When you see that word in a question, in the statement of a question, that's how you know it's about a significance test. And I know that this has to be a two-proportion z-test because it says proportion, and I'm going to have two samples, a sample of freshmen and a sample of seniors. So the word difference then tells you the direction of the alternative hypothesis. It's a not equal to rather than a greater than or a less than. Very important. In your parameters, the proportion of freshmen. So remember, what we're trying to do is to make a conclusion about the difference between these parameters. P freshman is the true proportion of all Illinois high school freshmen that use anabolic steroids. P senior is the true proportion of Illinois high school seniors that use anabolic steroids. So remember, the null hypothesis is always an equation. So we're going to take P freshman minus P senior. If there is no difference between these two parameters, the real difference is 0. We're looking for an evidence then of the alternative hypothesis, evidence that the true difference is not equal to 0. We had that word difference in the original statement of the problem. So now to check the conditions, we have two independent random samples, and we can think of them as independent of one another because they're from completely different grades. So here's the 10% rule. So again, 10 times 1679, 10 times 1366. Certainly there's more than 16,790 Illinois high school freshmen and 13,660 Illinois high school seniors. We check that in this context because this question is not about an experiment. This question is about an observational study. So now we have the success counts that were given to us in the problem, 34 freshmen and 24 seniors in the sample claimed that they had used anabolic steroids. So that means for the freshmen, there are 34, quote, successes, and there are 1,645 failures. For the seniors, there are 24 successes and 1,342 failures. So when you are listing the data, after you have listed the hypotheses and checked the conditions, you don't have to show your work by hand, but you have to show the data that you will use in order to draw your conclusion. So you should always name the test. This is a two-proportion z-test. There are two proportions, one for freshmen and seniors in Illinois, and proportions are always z-tests. We always use z-scores here. So this is the z-score and the p-value that we get from the calculator. So I'm going to show that to you. So again, to get that on your graphing calculator, if I get my mouse back, I can't seem to get my cursor back. So I'm going to go back to the other screen for just a second here and try again. Oh, there it is. Sorry about that. So press stat. We'll go to tests. We'll go to two-proportion z-tests. There it is. So for the freshmen, we had 34 out of 1,679. So then for the seniors, we had 24 out of 1,366. This is a two-sided alternative. So I will highlight calculate and press enter. So there is the z-score of about 0.54, and there is the p-value of 0.590. So there is our z-score, and there's our p-value. And so that p-value is very large. It's much larger than a level of significance of 5%. So this is not an unlikely outcome if the null hypothesis is true. So this is not unlikely. So we do not reject. We fail to reject the null hypothesis. So we do not have convincing, and then in red, I just copy the words out of the problem. Convincing evidence of a difference in the proportion of all Illinois high school freshmen and seniors who use anabolic steroids. So again, I urge you to use the words in the question to help you write a good conclusion. So for question number 18 then, we're simply going to build the corresponding two-proportion z-interval to see how the z-interval can help you come to the same conclusion as you did in the two-proportion z-test, because it was a not equal to alternative in the test. It was a two-sided test. So let's construct and interpret the 95% confidence interval for the difference between the population proportions. So we've already checked the conditions in the previous slide, so we just need to do the two-proportion z-interval. And the nice thing about this, if you press stat, we'll go to tests, and we'll go down to two-proportion z-interval, depending on how many options there are on your calculator. The shortcut to get to that option might be different. So two-prop z-interval, there's the command that I want. Notice, because we already did the test, it automatically copied over. It automatically stored and copied over the number of successes and the sample size out of each group. So the only thing that I need to change here, this confidence interval needs to be done at the 95% level, because we did our test at the 5% level of significance. So we'll highlight calculate and press enter. So the lower boundary for the true difference between these two proportions is negative 0.7%, and the upper boundary is about 1.2%. Again, I wrote them as decimals. So I wrote them as decimals in my confidence interval interpretation here. You can write them as decimals or percentages. It doesn't matter. So we're 95% confident that the difference in the proportion of all Illinois high school freshmen and seniors who use anabolic steroids is between negative 0.007, there it is, and then positive 0.012. So now this is the most important reason for building the confidence interval. This is consistent with the significance test that we just did, because notice, in the significance test, we did not reject the null hypothesis. We failed to reject the null hypothesis. Well, remember, the null hypothesis was that the difference between the two population proportions is equal to 0. Well, notice what's in this confidence interval. It is possible that 0 is the true difference between the proportion of all Illinois high school freshmen and seniors who use anabolic steroids, because a difference of 0 is actually in this confidence interval. The lower boundary is negative. The upper boundary is positive. 0 has been captured. Because 0 is in the confidence interval, this means the null hypothesis can't be rejected at the 5% level of significance. That's why it's so important that you write the null hypothesis as an equation equal to 0, because it's in this confidence interval. When I say it, because 0 is in this confidence interval, that's why the null hypothesis cannot be rejected. So that's why in our previous test, we were not able to conclude. We did not have evidence of a difference in the proportion of all Illinois high school freshmen and seniors who use anabolic steroids.